We want to find the value of c that will make this function continuous. Let's first look at the individual pieces and see what we know. We know the first piece is quadratic, and we know that quadratic functions are polynomials, and polynomials are definitely continuous functions over all real numbers. The second piece is a cubic, which is also a polynomial. So both pieces, the top and the bottom piece, they are both individually going to be continuous over all reals. Now let's look at their individual domains. The first piece, the first function, is going to be for x values less than 2. The second function will be for x values greater than or equal to 2. So imagine these two functions, we need them to meet up at 2 and they need to be continuous. And we're trying to find the value of c that will force the functions to be continuous at 2. In other words, we want the functions to meet up together and be continuous at 2. In order for the function to be continuous at 2, the limit must exist as x approaches 2. And in order for the limit to exist, we know that means that the left-hand limit must equal the right-hand limit. So we're going to go ahead and compute the left and the right-hand limits as x approaches 2 from each side. And we want the left and right-hand limits to be equal, so we will set those limits equal to each other. So if we are taking a look at the limit as x approaches 2 from the left, then we know we're going to be looking at x values smaller than 2, which will put us on the top piece of this function. And the top piece is the cx squared plus 2x piece. Now remember, I know this looks odd because we have two different variables. We have c and we have x. But remember, our ultimate goal is to find the value of c. So we are going to solve for c throughout this process. Now, to evaluate this limit, we'll do direct substitution, and we will substitute in 2 for x. So that will be c times 2 squared plus 2 times 2. In other words, 4c plus 4 is our left-hand limit. Now let's look at the right-hand limit. X approaching 2 from the right means we're looking at values larger than 2. That means x is greater than, in this case, or equal to 2. So we are on the bottom piece. So that'll be the limit of x cubed minus cx. Again, we'll do direct substitution. You'll substitute 2 in for x. And that'll give us 2 cubed minus c times 2, which will be 8 minus 2c. Now remember, we need the limit to exist as x approaches 2. Which means we need the left-hand limit to equal the right-hand limit. So now we can set the left and right-hand limits equal to one another, and that will allow us to solve for c. So solving for c, we'll add 2c to both sides. So 6c plus 4 is equal to 8. We'll subtract 4 and then divide by 6. And that will give us c is equal to 4 divided by 6, which is 2/3. So if c is equal to 2/3, then this function will be continuous. Now, let's check this on Desmos. So open up Desmos, and we're going to go ahead and graph this piecewise function, but we're going to be plugging in 2/3 for c. And it's just nice to get a visual and verify that our value indeed does work and creates a continuous function. So go ahead and open up Desmos. And let's graph our piecewise function. So we have 2/3 x squared plus 2x as our first piece, which is a parabola, but we're going to restrict the domain of this piece. So we need to find the curly brackets, which would be right here. And we only want the x values that are less than 2 for that first piece. Then let's graph the second piece, which is x cubed minus 2/3 x. And again, You want to find those curly brackets because we only want the piece of the graph where x is greater than or equal to 2. And right there you can see that we have chosen the correct value for C because the red graph, the parabola, it does meet up with the blue graph, which is part of a cubic. And indeed, I can draw the entire graph without ever picking up my pencil, thereby making it continuous.